Okay, so let's solve this problem. So this is an already written down this an objective. I believe in this case is let's just using this one, right? So this one right here. So we take partial derivative with respect to. So I'm going to call this as loss, total loss, which is a function of w and the w0. Right. So what we can do is we can take partial derivative with respect to w. So we know, and we always have this half a square and a square of the 2 norm of w. So this becomes the w plus summation of I from 1 to the n. It has two possibility. If this term is bigger, then I mean we're going to take partial derivative with this term. So this will becomes minus yi of xi transpose, and we have a lambda. So this is minus lambda yi of x of y transpose if yi x of y w plus w0 is less equal than 1. It will be 0 otherwise. So you can do similar things with respect to w0. So this, we don't have a term of w. This just simply becomes summation of I from 1 to the n of 0 and minus lambda yi. If yi x of y w plus w0 is less equal than 1, this is otherwise. Okay, so so we can write down this gradient. For the subgradient. So basically, we don't know precisely, and we don't, and this whole thing is, I'm almost everywhere like differentiable, except for one point when this quantity is like equal to 1, then and on one point that will be and then not differentiable. So we can actually calculate the subgradient and using gradient descent, directly, and trying to minimize these loss functions. So this is the bare minimum to work on using and stochastic gradient and descent method to solve these loss functions. We don't actually need to and make sure every point is differentiable, but at least should be piecewise so differentiable, such that we at least we have some subgradient information, like in these cases. So if we utilize this information, we can implement this from scratch right here. So this is what we are right here. So this is I'm going to run this. So this is the same data set that we already have. We will have an outlier points. So this outlier points right here. So you can see this is my outlier. So hypothetically, if we're using harm margin, it should have a line here. So that it's between this outliers and versus this point. So it will make this whole and the whole region and the margins to be really small. So it will be really bad. And as ideally, if we're using soft margin, it should draw the decision boundaries right here, such that this outlier point will be violated. And let's see how it works. Okay, so this is my prediction function. So this is basically, and we have talked about this before. This is my loss function. So this loss function is pretty straightforward. We have and we have and the norm of square times half, and then we add them together. So and add them under the condition and the maximum of this condition is 0. So that would be and that would be my loss functions. So here, this training is we're going to train everything. So with the stochastic gradient descent. So that means if this condition is satisfied, and they will, and that will, and this W will learn and according to the top gradient. So that means this contribution right here will be 0. We only have a contribution from W. So this, what we are going to have is just minus learning rate times of W here. If not, so if this condition is not satisfied, that means we are going to that means we are going to optimize with the second condition right here. So this gradient part will be minus lambda yi and xi transpose, and the bottom one is minus lambda of yi. So that's why in terms of gradient descent, I'm going to apply the second one. So with the this subgradient informations, we are going to discuss with the different conditions. When the condition is satisfied, we are going to using one gradient. If this condition is not satisfied, we're going to using a different gradient. So that's how we process this training for the soft margin SVM. Here we are trained with 500 epochs, and we have this learning rate and decays polynomially. Yeah, and of course you can change that if you need it. So this is what we have, and after this we see this and my W has this value. My W0 looks like that. So we can run. I believe my my lambda that I choose is 10. This is quite large. So we know if we choose like lambda to be large, that means so large lambda means large lambda means wait. Where is the right here? So if the large lambda, that means I want to emphasize this portion right here. If the lambda is small, that means I want to emphasize this point, right? Depends what we are trying to work with. All right, so if lambda is 10 right here, so you can see we choose this and we got this and the decision boundaries right here, and we have a 1 point, and which is yellow. This actually violate violate this classification. So this will give one error here, and these two are actually the margin boundaries. However, for those points right here, it's still being classified as black, and these points is still being classified as yellow, but those points already cross this margin boundaries. And then these points also cross this margin boundaries as well. So that means, this, and for these points, and the K of I will be bigger than 0 for these points, and that K of I will be bigger than 0 here. And then we can try with a different and lambda, and let's try with a different, and let's say lambda equal to 1. So you can see right here we have a more like violation of the margin boundary. So and with the lambda, so equal to and smaller, I want to emphasize my margin to be bigger and bigger. Yes, my margin is to be bigger and bigger. So I can allow certain point and across this margin boundaries, and more point to and across the margin boundaries. If we change this lambda into 100, you can see there will be less and less point that will be allowed to cross this margin boundaries. If we set this to be, and for example, right here, and we can set this to be super large, like 10 to the 4, this will be almost like an half margins. And because we know if lambda is super large, that means I will not allow to have any kind of misclassifications. So in some senses, that will be equivalent to say we want to work with and a half margin and SVM. So if we try the 10,000, you can see this actually perfectly recover the hard margins SVM situation that my margin so my boundary and so my decision boundary is this right here, and these two marginal boundary here, and passing these two and supporting vectors and supporting vectors, and we have a 2 supporting vector, one and a supporting vector here, another supporting vector which is the outlier of this and the blue points. So you can see right here. So this is actually perfectly recover the hard margins and so SVM. So in some senses, you can think about. So this is an universal and universal versal methods for hard and soft margins. So all we need is to choose different lambdas, and it can work out, for either soft margin and hard margins simultaneously. Okay, and of course, if you want to choose back to 100, this goes back to soft margin again. So as you can see with the 100, this is much more reasonable. That will allow 1 point to be misclassified, but the margin is it's really relatively large, and it will be more stable with the perturbation of the points. Okay, so now the question is how to choose this lambda, right? So, and of course, that will be on the cross validations. So you are going to using cross validation to choose the best lambda. So this, for the testing data set. So basically, if you are giving a very large data set, you can using either holdout or pay for the cross validation or simply cross validations to find out the best parameter for lambda. Okay, so I'm not going to demonstrate that. I assume everyone already know how to do it from scratch, and you already did a lot of and related work. So in the previous 2 homework. All right, so that's all I want to talk about for the SVM soft margin. In the next lecture, we're going to talk about a kernel method. Again, so this is the kernel method. Again, but for the classification problems instead of the regression problems. All right, so that's all.